Hey guys, today I will be talking to you about entropy. Entropy is the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. In other words, it is a measure of molecular disorder or randomness of a system or chemical reaction as a whole. Before I go too far, let me define what a system is. A system is the compounds, molecules, and energy being studied or observed. For example, 2H2 plus O2 yields 2H2O is a system. Another example is a chemical reaction taking place inside of a beaker. The beaker and all of its contents are the system. Everything else besides that is the system's surroundings. Okay, now back to entropy. Let's take a look at this diagram. There are 4 molecules in a container. These 4 molecules can occupy different positions in different orders at any given time. Right now you see them in this formation, but they can also look like this, or any other order you can think of. That is because of entropy. In this system, we see a larger container with more molecules. These molecules can look like this, or thousands of other combinations. Which entropy is greater? The one of the system to the right, or the one of the system to the left? The entropy of the system to the right is higher than the one to the left because it has more molecules, more volume, and therefore more randomness. This system can occupy more states than the system to the left. These 2 examples of entropy demonstrate microstates of the macrostate. So, what do I mean by that? A microstate is just one of the several different possible arrangements of molecules and kinetic energy at a particular state of a system. Therefore, a macrostate is all of the microstates. An increase in microstates means an increase in entropy. The system on the right has more microstates than the system on the left. This lines up with our previously made observation that the entropy of the system on the right is higher. Make sense? Let's look at entropy another way. Say you have a glass of water at room temperature with a few ice cubes. Will the water turn to ice, or will the ice turn to water? You probably guessed that the ice will turn into water, which is correct. But let's take a closer look at the H2O molecules and see why it can't be the other way around. All of the molecules are bouncing off of the cup or other molecules. They all have an average momentum or rate of kinetic energy. Let's say that a few molecules bump into each other and the momentum is transferred from one molecule to the other. Now, a few molecules have an above average momentum and a few have a below average momentum. The 3 molecules that have a low momentum come close enough to form a lattice structure and freeze into an ice cube. That looks like this. The molecules with more momentum move around this newly formed ice cube and gain heat. While this explanation makes the idea of spontaneous heat transfer from cold to hot seem possible, it isn't, and that is because of the second law of thermodynamics, which states that there is an inherent direction in which any system moves if it is not at equilibrium. The total entropy of a system either increases or remains constant in any spontaneous process. You might be thinking, well, why can't it decrease? The answer is that there needs to be some kind of outside force or another system interacting with the original system for that to happen. Let's go back to the glass of water with ice cubes. If you leave that glass in your room and come back in an hour or so, all of the ice will be gone. That happens spontaneously. In order for the remaining water to freeze, energy needs to be taken away and the temperature of the water surroundings needs to be decreased. When energy needs to be added or taken away artificially, the system is no longer random or spontaneous, and therefore entropy is no longer involved. You can calculate the theoretical entropy, but it can't be experimental. This also explains the fact that for every spontaneous process, we can imagine a reverse one that is not spontaneous. An example that demonstrates this and relates entropy to equilibrium is the reaction between sodium and hydrogen. The equation for that is N2 gas plus 3H2 gas yields 2NH3 gas. That occurs at 472 degrees Celsius. Say the molarities for this reaction are 1, 1, and 3. Using this equation, at this temperature, the equilibrium constant of the reaction is 0.105, but Q equals 0.0370. Q is less than K, so therefore the forward reaction dominates and the system moves spontaneously towards the equilibrium constant by the formation of NH3. The opposite process, or the reverse reaction, is not spontaneous at 472 degrees Celsius. Based on this, we now know that thermodynamics can tell us about the direction and extent of a reaction, but nothing about the speed. As you have just learned, randomness is expressed by entropy, S. The more disordered a system, the higher the entropy. Another example is the reaction of propane gas. The enthalpy is negative 2,202 kilojoules. This reaction is obviously spontaneous and extremely exothermic. Just because a reaction is exothermic doesn't mean it is spontaneous. Now, a question that might be popping up in your heads is, can entropy change? The answer is yes, it can. As stated in the second law of thermodynamics, the total entropy of a closed or isolated system can increase or remain the same, and the entropy of an open system can increase, remain the same, or decrease as long as there is an increase in the entropy of the surroundings. This is because the total entropy of the universe can never decrease. An isolated system is one that does not exchange energy or matter with its surroundings. A closed system is one that exchanges energy but not matter. And an open system is one that exchanges energy and matter. When a spontaneous process occurs in an isolated system, the system ends up in a more random state. While this is the case, we rarely deal with isolated systems in the real world. We usually deal with systems that exchange energy in their surroundings in the form of heat or work, open systems. Something to note is that while the energy of the universe is conserved, which is based off the first law of thermodynamics, that energy can neither be created nor destroyed, the entropy of the universe is always increasing, and we are constantly moving towards a universe with more possible states. In fact, we all contribute to that increasing entropy. As living beings, we require a constant input of energy to maintain order. Without that energy, we wouldn't exist. Every year, the population increases, which means an increase in energy is needed. Since one of the definitions of entropy is how the energy of the universe is distributed, an increase in energy in the universe to sustain living things causes an increase in entropy. Okay, so back to figuring out change in entropy. Let's think back to that glass of water I was talking about in the beginning of the video. Let's say we put that glass in the freezer. Theoretically, the entropy of that reaction will decrease because energy is being exchanged and the system is becoming less random. Change in entropy has three parts. 1, a number. 2, a unit in joules per mole times Kelvin. And 3, a magnitude of charge and a sign, which gives direction. A positive entropy means that randomness or disorder is increasing, and a negative entropy signifies a decrease in randomness or disorder. The equation for a change in entropy is S of reaction equals S of products minus S of reactants. Let's look at an example. Liquid H2O yields gaseous H2O. 1 mole of water is 18 grams, which occupies 18 milliliters as a liquid and 22.4 liters as a gas at standard temperature and pressure. Compared to the liquid state, in the gaseous state, the water molecules are spread throughout a larger volume. Because of this, the change in entropy is positive. Let's look at one more example using the equation. What is the change in entropy when calcium reacts with water? This is the equation for the reaction after it's balanced. The entropies of the substances in joules per Kelvin are 41.4, 69.9, 75.9, and 130.5. After doing the calculations, we get that 181.2 yields 206.4. Next, we use the delta S formula to find the change in entropy, which ends up being 25.2 joules per Kelvin. Something else that is very important is Gibbs free energy. Free energy is the energy available in a system to do useful work. How spontaneous a reaction is involves two thermodynamic concepts. 1, enthalpy, and 2, entropy. Gibbs free energy allows us to use change in enthalpy and change in entropy to predict how spontaneous a reaction will be. To find a change in free energy, you need to use the equation delta G equals delta H minus T times delta S. To look at this as it relates to enthalpy and entropy, we can say that a process driven spontaneously towards equilibrium both by a decrease in enthalpy or energy and an increase in randomness will have a negative free energy. A change in free energy that's less than 0 means that the forward reaction will be spontaneous. A change in free energy that's greater than 0 means that the reverse reaction will be spontaneous. And lastly, a change in free energy that is equal to 0 means that the reaction is at equilibrium. An example of free energy change in a spontaneous reaction is a boulder rolling down a hill into a valley. Potential energy in a gravitational field drives the boulder until it reaches a state of minimal potential energy in the valley. Here, the system is at equilibrium. Like this, in any spontaneous process at standard temperature and pressure, the free energy always decreases. We can look at the reaction N2 plus 3H2 yields 2NH3 like this too. Once the equilibrium constant has been reached, there is no further spontaneous net formation of NH3. In order to form more of the product, the free energy must increase. So, what should you have taken away from this video? The first law of thermodynamics is that energy can neither be created nor destroyed, and the second law is that there is an inherent direction in which any system moves if it is not at equilibrium, and the total entropy of a system either increases or remains constant in any spontaneous process. Entropy is a measure of molecular disorder or randomness of a system or chemical reaction as a whole, and it cannot decrease spontaneously without an external force. The equation to figure out a change in entropy is S of reaction equals S of products minus S of reactants. Free energy is the energy available in a system to do useful work. The equation for finding a change in free energy is delta G, Gibbs free energy, equals delta H, change in enthalpy, minus T, the absolute temperature in kelvins, times delta S, which is the change in entropy. Entropy, free energy, and enthalpy are all related. Exothermic reactions with positive entropies will be spontaneous at all temperatures, and the change in free energy is less than zero. Exothermic reactions with negative entropies are spontaneous at low temperatures, and endothermic reactions with positive entropies are spontaneous at high temperatures. And lastly, endothermic reactions with negative entropies are not spontaneous at all temperatures, and the change in free energy is greater than zero. I will leave you all with this question. Will the second law of thermodynamics ever be proved wrong or violated? Physicists say they found a loophole in the second law which could make it possible for entropy to decrease with time. So that's something to think about. I hope this presentation helped you understand entropy and free energy.